In this video, I'm going to be talking about how we get from silicon to computers. So to start off with, the first thing we're going to do is we need to understand that there's a process called doping where we can take pure silicon and we can add in small amounts of impurities, usually phosphorus or boron, and we can either add in additional electrons or the concept of holes. When we stick these together, we can get a boundary layer that only allows electricity to flow in one direction, right? So this would be where I usually use my Harry style reference, right? Get out of my head. What's the, is that what it was? Yeah, that, right? Anyway, so, you go in one direction, yeah, diodes, that's what they do. Right, you should know that at this point. Okay, what do you use diodes for? Well, there's a whole bunch of different kinds of diodes. The most famous is the LED. The symbol for the diode is this triangle with a line on it. If you buy a non-light emitting diode, it will have a band on the cathode side of the diode. And yeah, we use them because they only allow electricity to flow in one direction. So that video is explaining the same concept. The electricity it flows from positive to negative. The electrons flow in the opposite direction. And when we close this switch, it will only flow in one direction. Okay. There are different kinds of diodes. Electroboom has a whole video on that. Right, we're only really interested in Zener diodes, and Zener diodes allow electricity to flow after a certain voltage. Right, he goes into it more detail than we need in the HSC, but always good. I'm a big fan of Electroboom ads, videos. Okay, another video I like is technology connections. And in this technology connections video, he shows a old radio, a crystal radio, and he shows that the radio is made of crystal called galena.
Well, it's a semiconductor. It conducts electricity better in one direction where it's from. It's called a crystal radio because it works using this, a crystal made of galena. Why do we need this crystal? Well, it's a semiconductor.
Galena, okay. I'm going to try and avoid using any audio because, I hate getting, the YouTube sends me angry letters. Anyway, so, that's not really true, but anyway. So, they use it because it's a semiconductor that only allows electricity to flow in one direction. That's important. We won't learn about that until year 12. It's the last topic we do in year 12. So we have just about to start talking about demodulation. The circuits that you can use for demodulation, you can buy from JCAR. They're pretty simple. It's like a hobby that people like to do is to make crystal radios. And here's a video on how to make a crystal radio. If you want to make it, but the big thing is that you need, so this crystal, right, only allows electricity to flow in one direction. What do we call something that only flows in one direction? Starts with a D? A diode is the answer. Okay, but also, if we continue to watch that technology connections video, he goes on to say that the thing they needed as well is they needed a vacuum tube, and the vacuum tube would act as an amplifier. Now, those of you who have watched this video, which is actually the one that we saw before we clicked on Harry Styles, this was with the creepy arm robots. I'll click on that in a second. We can also use semiconductors, right? This increase in electrons or holes, we can use that to make a switch, or we can use it to make an amplifier. So that's what the vacuum tube was being used for, as an amplifier. So yeah, this is the video where we've got these unusual looking silicon atoms, and we can see the addition of doping creates holes or additional electrons. And at the end, we can get fancy and we can have a double amplification. Here we can see this object here we call a transistor. So we've replaced the vacuum tube with a transistor. Oh, I just closed that accidentally. I'm not sure what it was closed. Oh, okay, so this video here, the transistor, the invention that changed the world. So this is real engineering. And he starts off by talking about vacuum tubes. I don't think he explains the vacuum tube as well as technology connections. He only shows big computers that use these vacuum tubes, and that these days we have silicon wafers. And one of the things that ANSTO does three things. They make neutrons for They make neutrons for electron microscopes, except they're not electron microscopes because electrons are less good because they're polarized. and they make medicine, they make chemotherapy medicine, and they dope silicon. They're the three main things that ANSTO does. ANSTO doesn't cost us any money because people want to buy doped silicon, right? And so by doping silicon, we can get these semiconductors. Here we have two layers. We have an N layer, a P layer, and so we call the P layers the side that has the holes. The end one is the one that has the extra electrons. And if we have three layers of it, we get a transistor, all right? Okay, so we know how we can get this silicon. Now, if we keep watching this video, he does this thing where he talks about where we can add some numbers, and they're always ones and zeros, and we've got some different symbols here, and we can add those, take those different symbols, and we can use that to make computers, right? He talks a little bit about Moore's law, and there's a problem with Moore's law, which we're going to get to. Okay, so we're done with that video. I'm not going to close any of these links because I'm going to copy the links later. So we saw that this is what a transistor looks like, and this is the symbol for a transistor. We saw that the NPN, the P just means the section that has the transistor, that the silicon semiconductor that has additional holes, right? The silicon has extra holes, and the N has extra electrons. I expect you to have already watched those, but I'm giving a brief update. Now, this excellent video by Kurt Gesagt, in a nutshell, it talks about, okay, so computers contain modules, and modules contain logic gates, and logic gates contain transistors. And we can see that transistor symbol. So we talked about that a second ago. I always think of a transistor, I always draw it sideways, and I think of it as looking like a picnic table with an umbrella. And the umbrella is the switch, right? And in this case, we can see instead of the umbrella, we've got a finger that's pressing the switch. And so it shows, yeah, we can press on or off if the button presses it. Now, we store all of the information as ones and zeros. So we talked about that before. We're going to come back to the ones and zeros and that stuff. I'm going to put that at the end. Okay, we may actually have been ready for it. Transistors. Okay, so what we should talk about now is those symbols we saw on this video, right? So we saw, I did want to keep going, sorry. Okay, so we've got ones and zeros. Yeah, things can either be set as ones and zeros. They're talking about different numbers of bits and how much information we can store. So if we have 2 bits, we can store 4 bits of information. 7 bits sends 128 ASCII symbols. 32-bit, 4 million RAM addresses. And here we have these symbols, right? Called logic gates. These are 3 of the 4 logic gates you need to know for the HSC. So we have AND gates. The idea is that if we just think of this as being the positive and this being the negative, we have 2 switches, and as long as both switches are closed, right, the thing is going to turn on. But the idea is that if only A is turned on, the thing won't turn on. Right, they both need to be turned on for it to work. Right, and then we can combine all of these to make something add. Right, and we're going to look at that at the end of this video. So we can combine those together to make a module, and then modules. What are they saying here? Once you can, so you can do things like add and multiply, and once you can do adding and multiplying, it's all pretty simple, right? And once you can do that, you can start doing pretty much everything. Now, this video goes on to talk about how this is the size of a transistor relative to the size of a HIV virus and compared to the size of a red blood cell. And the problem is, at this stage, we're actually dealing with individual electrons. And the problem is, because of quantum physics, which is beyond the scope of this course, the problem is that we're getting, because of Moore's law, which real engineering talked about. So at the end of this video, he showed a picture of some guy Moore's. Where did they show him? Okay, Gordon E. Moore. I believe he was from Intel, and he made the prediction that the number of transistors on a chip was going to double every 2 years. And that held pretty true until about now. And we're now at the point where that's no longer true. And so Kurt-Kazak's video is talking about an idea that we can do instead, which is using quantum computing, which is well and truly beyond the scope of this course. Okay, so what we saw in that Kurt-Kazak video is what we want to focus on is these gates, right? So we're going to come back to bits in a second, or binary in a second. What we're going to focus on is we've got these different gates. So we looked at the AND gate, which is pretty simple. The OR gate will work if either A or B is switched on. NAND will only work if N and B are both switched off. And then we have XOR, which is not even in the HSC, but we're going to talk about anyway. Okay, so to start off with, we're going to watch this video. And it shows with water the idea that the water only goes into the sink if they're both on. I'm just going to reset that. Reset. Okay, so the water only goes in if both taps are on. Yep, so it's an AND gate. Or the water goes in if 1, 2, or the left one, the right one, or both are on. The XOR, it only works if exactly one is on. So we said that's not part of the HSC. So here's what we do have to know in the HSC. This is all the electronics we need to know for the HSC. We need to know AND, NAND, OR, and NOR. Now we haven't talked about NAND and NOR, but how I like to think of it is I just like to think of NAND is just an AND with a not dot, right? The not dot flips it and reverses it. Normally in class, I would play Missy Elliott's Work It because she has a thing about flipping and reversing it, right? But, you know, I'm not going to show that now because, you know, demonetized. Okay, so they're the four that we need to know. So let's have a look. Okay, so we've got this introduction to logic gates. Yeah, okay, we'll go with that here. I did have another introduction to logic gates that it looks like I've lost. I'll have to accept it. Okay. So what?
Logic gates are electronic circuits that manipulate voltages.
Okay, so we see how we used to start with vacuum tubes. We've replaced vacuum tubes. We're doing better than that now. We now use transistors. We sometimes use resistors. These days, we can print them onto silicon chips, right? Literally millions of these on something the size of your fingernail. That's the symbol for a transistor, right? The picnic table. That's the symbol for a resistor. And this is how we draw a NOT gate. The idea is that a NOT gate just flips and reverses. Now, there are three basic logic gates, and I did have the logic gate squad. Oh, here we go. Okay, the logic gate squad, right? I like this video because it's, you know, it's kind of corny, right? But this is the NOT gate. This is the OR gate. This is the AND gate, and together they are the logic gate squad. I'm literally quoting what the video says. Okay, so they're the three. We can use these gates to make everything, right? So we can use those gates to, all the computers just rely on those gates. So first of all, let's just explain what those gates do. So the first one here, the NOT gate just flips it and reverses it, like Missy Elliott, right? So the idea is that if we had a 1, now 1 just means high voltage of electricity. Suddenly it has low voltage of electricity. And sometimes it's really odd to think, how does that work? How does a computer make it have low electricity? How does it turn the electricity off? Well, we'll get there, don't worry. Okay, so we can show these in what we call truth tables. The idea is that if the input is 0 or off, suddenly it turns on. And if the input is on, suddenly it turns off. Okay. This is how it works, but we're going to explain that in a second. Here we have an AND gate, right? So an AND gate, remember the AND gate looks like a D and they have to both be on. So if we have one is on, nothing. The other one's on, nothing. If they're both on, bingo. Now I always like to talk about this as being like a bouncer, and the bouncer looks to see if you're on the list. And it says, Kate's on the list. Yeah, sorry, you have to both be on the list to get in, right? Lily's on the list. Sorry, you have to both Kate and Lily. You're in. Then the girls can go out and party, right? Again, we're not going to worry about the wiring just yet. Okay, the OR gate says Kate's on the list. Don't worry, Lily, you can go in too, right? Lily's on the list. Don't worry, Kate. You can go, you get a +1. Now, the not dot, I always like to think is like the crazy manager who comes along and she just hates the bouncer, and whatever the bouncer says, the not dot just flips it and reverses it. You're both on the list? Too bad! You're out! Right? Just whatever the bouncer says, it's the opposite. Right? That's what the not dot does. Okay, so we've got these tables. Okay, pretty happy with that. Now, what we can do is we can use these things in integrated circuits. Integrated circuits are devices that have all of these transistors already wired in ways that are easy for us to use, easy for us to work. So if we're making our, say, crystal radio, right, we can just plug in our parts because they're already ready to go, right? Now, crystal radio is super simple, so that's not a great example, but we're going to look at some examples, and we're going to start with this 555 timer. And you might think, why do I want a timer? What would a timer do? Well, here we have, we're going to explain what the timer does first, and then we'll explain what it does. Okay, so the 555 is an integrated circuit that consists of 25 transistors, 2 diodes, and 15 resistors. Right, so we've learned about all those things. We know diodes, get out of my head, you go in one direction, right? Hey, Uncle Harry, we want to dance with you. And we have transistors, which look like tables, look like picnic tables, and we know that they act as switches and very rarely amplify. Well, not rarely, but sometimes amplifiers. But we're really interested in the switch component. That's what our focus is, on the switch. And this has got 25 switches in it. I didn't see all those, I can only see one transistor here. That's because these other things, they combine. We're going to see that he's like, oh, that green thing here, those green things, they combine, they can contain all those transistors. Right, and here we have the blue one, and here we have the purple thing, and here we have the orange thing, and so that's how we get our 555 timer. Now I said, what would we ever want to use this sort of thing for? Well, let's say you want to make a diode flash, right, an LED flash. Pretty cool, right? How cool is that, right? So we can use this 555 timer to make it flash. Now you can watch how to wire it, but the idea is if you want to make something flash, you can use a 555 integrated circuit, right? Okay. The next thing we're going to talk about is the ones and zeros. Now, in class, I will show you the fantastic song Rowboat Boogie by Flight of the Conchords, right? And it has a binary solo, 0000001, 0000001. Anyway, I'm kind of spoiling it, but you know. So the thing is, what we can do is we can use transistors as, imagine if you wanted to send a message, right? You had coded messages based on how many lights were on. Now, the example I always use is, I've never actually bothered looking this up, and I'm going to do it now. Full house, recording, red light. Let's see if I can find... Okay, great. I love that we live... So I do generally say that the internet was a mistake, but I'm going to say that in a TV show called Full House, the prequel to Fuller House, Uncle Jesse, right, who, he's this one here, the handsome one, he was a singer and he was recording downstairs. The problem is that the girls, I'm not sure which one, we'll say all three of the girls, they kept interrupting, they kept offering them like a sandwich and all of these things, and they kept ruining the recording because they didn't know that he was recording. So what did they do to solve it at the end of the episode? They put on a red light, and when the red light was on, it meant, don't come in, I'm recording. I should probably do that for my, my videos, but I don't. Anyway, so if you have one light, you can send one message, right? Well, actually, you can send two messages. You can send, I'm recording, or I'm not recording, right? But imagine if you had a red light and a blue light, right? How many messages could you send now? 4, right? Because you could say, let's say the blue light was the sandwich light, right? So what you could say then is you could say, no lights means I'm not recording and I don't want a sandwich. The blue light means I want a sandwich. The red light means I'm recording, and the red light and the blue light means I am recording, but I still want a sandwich, right? So we can send 4 different messages. Now, what about if we're using these we're using the transistors as switches, right? Now, if we had 4 transistors, we could, if we're just counting the tally system, right, we could only send 4 messages, right? That's pretty stupid, right? So well, that's an inefficient use. So what we're going to do instead is we're going to use binary, right? Instead, we can send 15 messages, right? With four lights, right? If we had 4 lights, Uncle Jesse could send 15 messages. Now, you'd have to know what those 15 messages were, but you could send 15 messages. This is through what's called binary, right? This is the zeros and the ones. When the transistor is on, we set the value to 1. When the transistor is off, we set it to 0. Okay. And the idea is that I'm now going to jump around. It's like base 10. It's like base 10, but in base 10, what we have is a 1 column, a tens column, and a hundreds column. And so we can say this is 623.
If you add those all together, we've got 263. Notice how each column has a different multiplier. In this...
Okay, but if we go instead to binary, instead we're going to have a 4s column, a 2s column, and a 1s column, right? And we see, okay, we have 1 in the 4s column, so 4. We have nothing in the 2s column. We have something in the 1s column, so we're going to have 5. Total of 5, right? And then we can get bigger numbers, right? It goes up to 8, 16, 32, 64, 128. Now, any of you who have ever bought a thumb drive, you might recognize those numbers, right? They might be the sorts of things that you've seen before. You can add these numbers too, and it's pretty simple, right? Because you're showing 2 as, so if you have 1 plus 1 equals 2, you put a 0 and you carry the 1 into the 2's column. Right, so it's actually fairly easy to do this addition, right? And those videos will go through it. Now, what we're going to look at, we're going to start there, and we're going to say, well, there's the columns. Okay, so what do we use this for? So if we have 8 transistors, we call this a byte, and we can store any number up to 0 to 255. So if we include 0, we can actually include 256. Right? We can spell in binary using something called ASCII, right? So we use this combination of 8 bytes to do these different symbols and letters, right? So A would be written like that. And this is why we use chunks of 8 a lot of the time. Now, we don't have to use chunks of 8 all the time because sometimes we get things that are more powerful and we need to have bigger than just 255. So what we can do is we can have 2 bytes worth of storage, right? And so we had 8-bit computers and we had 16-bit computers, right? Were like the SNES. The SNES was 16 and the Super Nintendo, I believe, was 32. Your computer is 32, and then they had the Nintendo 64. Modern computers are now 64. And then I don't know if you have 128-bit processors. I don't want to make that assumption. Okay, so that's kind of what they're talking about here. Okay, so, computers, all the colors in computers, every single pixel is denoted by a 3 bytes worth of information. A red byte, a green byte, and a red, well, usually we say RGB, so red, green, and blue byte. Right, so 3 bytes for every single thing. You can also learn about, say, how hardware storage works, but that's not what we're going to focus on. Okay, so what we're going to do now is we're going to count in binary. So we've got 1 plus 1, we carry the 1, 2, 3, 4, 5, 6, 7. Now 8 is a new byte. 9, 10 is 8 plus 2. Okay, so 8 plus 4 is 12, and then 16 is a new byte, 16 plus 1, 16 plus 2, 16 plus 3, 16 plus 4, okay, and we can stop at 20. But how many can you count on 2 hands? The answer is between 0 and 1,223 on 2 hands. Okay, so what we're going to do, now we've already looked at this video representing the thing binary. What do they talk about? They talk about how we need to use double-bit integers, or double-byte integers, and how, Unicode is a way so that different languages didn't get their languages mixed up. Okay, so now what we're going to do is we're going to make logic gates from transistors. Okay, so...
And there's an symbol for it over here.
This video, so first of all, is showing how we can just have a button and we're going to use the transistor as a switch. We already knew we could use transistors as a switch. The idea is that when we apply electricity to this B, right, the base, or when we apply electricity to the base, it's going to turn on our LED. So the electricity is flowing this way, right? From the positive to the negative, or the current is flowing this way. The electrons are flowing opposite to that because Ben Franklin got it wrong. And what he's saying is that when we press that button, it instead will it'll change the flow and it will make the LED light up. Now, for the NOT gate, what happens here is they're saying that it's always on, but when we press this, when we press the button on the transistor, now it will flow through the path of least resistance, and because it flows through the path of least resistance, it doesn't flow through the LED anymore. Press the button, doesn't flow through the LED anymore. Okay, so we're going to flick back a little bit between these, and we're going to say, okay, if we want to have an AND gate, we saw that before. An AND gate is like having two switches, and if we close both switches, the light turns on. So if we go to this video,
Three fundamental operations.
So she says three fundamental operations. We've got NOT, AND, and OR, right? Like the logic gate squad. The first thing we're going to do is talk about NOT, and we're going to say, let me see Elliot flip it and reverse it. Whatever we had coming in is we're going to reverse it. Now the idea is, she says, first of all, if we have a transistor, the idea is that the transistor doesn't allow electricity to flow unless this control wire, the base, has electricity. You'd think of it being as like a tap. If the tap's not turned on, the water doesn't flow. Now in a NOT gate, what happens is you can kind of think it as being a tap that goes just to the drain. So the idea is that when we so she explains that here. So the idea is that NOT gate. Okay, so our output is up high. So if we turn the tap on, instead of the water flowing to where we want it to go, instead it's going to go out the outlet valve and it's going to flow out into the garden, right? So that's why that's how a NOT gate works. If we had a pipe, and the idea is that we want the water to flow here, but if we have an outlet pipe, instead it's going to flow out to the garden. Yep. Now that's actually a good analogy because we use the term ground to say the direction that the electricity is flowing towards. Okay, so that's a symbol for ground. Okay, so we've got the NOT gate. Next thing we're going to look at is the AND gate. So we've just looked at the our symbol there for AND, and the idea is that for our AND gate, both switches have to be on, and we can see our transistors that look like upside down picnic tables. If they're both on, then electricity flows. Okay, so we can make an AND gate in this video here. So we can see that we have the electricity flowing from the high to low, right? So if this is the ground, it's flowing through, and it will only flow, electricity will only complete a circuit and flow if both transistors are plugged on. And sooner or later, he's going to press a button. Okay, there we go, and it worked. Now, we also have an OR gate. The OR gate, he's got the wiring for the OR gate, and we'll have a quick look at the way we can depict it is because it's in parallel. The idea, the first one's in series, an AND gate is in series, but this is in parallel. If A is closed, it'll go through A. If B is closed, it'll go through B. Here we have an OR gate, right? So it's showing the same thing. It's showing the true transistors upside down and in parallel. And as long as one of them are on, or if the other one's on, or if they're both on, it will work. Okay, so, and if we go back to our circuit, we can see here, he presses the button, and it doesn't matter which button he presses, the LED will switch on. There and there. He didn't demonstrate that you can press both because an exclusive OR gate, which we'll talk about in a second, if you press both, it won't work. Okay, so I don't know if he does do an exclusive OR gate. I think he does, actually. Yeah, okay, so he does have an exclusive OR gate. One works, but see, two, when he presses both, it didn't work. It worked for a second and then stopped working, right? Because I think he was still actually holding one. So it looked like he was holding both. Okay, so the idea is, in this video, they show the exclusive OR gates, and they show we can build an exclusive OR gate like this, with an AND gate, an OR gate, a NOT gate, and another AND gate. Now, because this is so common, it has its own special symbol. The exclusive OR gate has its own special symbol. She uses in this video, she uses the term the AND looks like a D, the OR looks like a spaceship, the NOT looks like a triangle with a little circle with a NOT dot on it. Okay, because these are so commonly used, it has its own symbol, which she says looks like a smiley face. Okay, here's a circuit diagram showing the application of exclusive OR gates. Okay, okay. So we also have we don't. You'll remember that exclusive OR gates are not in our list of the 4 that we need to know. Yeah, not in the 4 that we need to know. So what we're going to look at is we're going to focus on NAND gates. Now, NAND gates are really great because NAND gates can be used to make everything. So this is a wiring diagram for a NAND gate, and we can buy sets of NAND gates ready to go in an integrated circuit. In this case, it's not the 555 integrated circuit, it's the 7400 integrated circuit, right? That just has a whole bunch of NAND gates. It has 4 NAND gates ready to go. And you can use NAND gates to make everything. Every other gate can be made from NAND gates, which is kind of a cool property of NAND gates. So this video shows the wiring of a NAND gate, what it looks like, and it shows the layout for, if we wanted to watch that video, we could see him wire the, actually, it might be interesting just to see that. So it's on, if that's pressed, nothing happens, but if they're both pressed, it turns off, right? Now, I try not to think of it that way. I just think of it as an AND gate and I flip it and reverse it. But that's a NAND gate. It's not entirely true, but you could think of your brain as, I always think of the synapse connections in your brain as NAND gates. That's not true, right? Because it's not, our brains aren't binary. They can have like high and low. It's a bit more complicated. Okay, so with XOR gates, they're the 7486 IC, so they're labeled like that. And we can use, this guy here, he's used this computer, he's bought some 7486, so 7486 integrated circuits, which we saw here. That's what they look like, that's the wiring diagram. And he's going to use 4 of them, and what is he going to do with it?
So we have 2 of these chips, each one has 4.
And he is going to show you how to wire this up. And when he's finished wiring it, what he's going to do is he's going to add some numbers in binary. Okay, so he's going to add 7 plus 10, right? So we know 10 is represented as 8 plus 2, that's 10, right? And 7 is represented as 4 plus 2 plus 1. If you don't understand that, you need to go back and look at the binary notes. So the answer should be 17. So with 17, he's going to do it as maths. He's going to say, well, 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. 0 plus 1, or sorry, 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. So what we get there is 16 plus 1, which is 17. Hey, it worked. Now, well, let's see if his machine works. So what he's going to do is in the first digit, right? So this first digit here, this first pink thing is going to be his first digit. He's going to set it as 1, 0, 1, 0. And then the second one, he's going to set it as, and you can show, he's saying like, see how the colors already show up because he's adding 0 to it. That makes sense. And then he's going to put on the other switches. So he's going to get 0, 1, 1, 1. And suddenly, that's pretty cool, right? And that's the basis of all computing, right? Once we can add, we can then multiplying is just adding fast. And once we can do that, we can kind of do everything, right? We can get a set of rules. Now, in the last, how I've got, so since 2004, I don't know if there were any before 2004, but here are all the logic gate questions that have been in the past HSC. I'm not going to go through them. But they're pretty consistent. We see them fairly often. I mean, I like this one because it actually shows the transistors. Yep. So this one here, we'll keep going. Doesn't like that one. there's just too many, right? Anyway, so if you want to practice some more, I have this page here. It has NOTs and XORs, right? So that, you know, they're not likely to be in the HSC. If you really want to practice heaps and you're okay with NOTs and XORs, this game, Make It True, is on both Android and on iPhone. I just went looking for diodes earlier. We already looked at that. Okay. Well, so this is, I mean, ultimately, I think what I wanted to finish on is this computer, right? Now, it's not a fantastic computer. There are videos you can watch of people who make computers out of dominoes, and that's pretty cool. What you can do is you can use dominoes to set up AND gates, NAND gates. You know, you can use dominoes to set up different logic gates, but we don't need to do that. We can see here that we can buy logic gates. We can buy ICs, the integrated circuits that have logic gates, and more importantly, we can go and buy things like Arduino microcontrollers that have programmable ICs, right? So PICs, and so that way you don't need to do any hardwiring. You can just do the maths on your just on a software. So an Arduino these are good if you want to do prototyping, whereas when you actually want to go and make something and you want to make lots of something, it's way cheaper just to buy the actual ICs that you need rather than the integrated circuit. Rather than a programmable integrated circuit. Okay, so hopefully that should be a good introduction on how we get from silicon to computers through the magic of doping and logic gates. Or as he says in this first video, the science of semiconductors.